Welcome to sub-module 2 of 3 in our Introduction to Torque and Drag. In this session, we will explore the fundamentals of torque and drag, their role in drilling operations, and how understanding these concepts supports better well-designed drilling efficiency and operational problem solving. On this slide, we see the learning objectives specific to sub-module 2 of our torque and drag discussion. By the end of this module, you should be able to clearly explain and define side forces, as they play a critical role in generating torque and drag in the wellbore. We will also cover friction factor, which is fundamental in modeling drag behavior and understanding how drilling fluids, borehole conditions, and contact surfaces influence resistance. Another key objective is to understand the causes of torque and drag. Recognizing these causes is essential for anticipating drilling challenges, particularly in deviated and extended reach wells. Additionally, we will examine torque and drag monitoring and management. This includes how to interpret field measurements and use them to diagnose potential hole problems before they escalate. Finally, we will introduce the broomstick plot. This is a simple yet powerful diagnostic tool for visualizing torque and drag, as well as for comparing actual field performance with predicted values. Okay, so let's work through the subject on the coefficient of friction and friction factors. On this slide, we examine the fundamentals of friction as applied to torque and drag in drilling. First, the frictional drag force is proportional to the normal force acting between the drill string and the borehole wall. In practice, that normal force results from the weight of the string, wellbore curvature, and side forces generated at higher inclinations. The coefficient of friction, often denoted by a mu, is defined as the ratio of frictional force to normal force. Importantly, this coefficient is independent of the apparent contact area, meaning that drag is governed by surface roughness, formation characteristics, and mud lubricity, not by how much surface is in contact. The angle of friction is simply the arctangent of mu. For example, if mu equals 0.4, the angle of friction is 21.8 degrees. From this, we calculate the critical inclination as 90 degrees minus the angle of friction, which here equals 68.2 degrees. This is a critical concept because it indicates the maximum hole angle at which the pipe can slide into the wellbore under its own weight, without assistance from additional mechanical or hydraulic means. Beyond this point, pipe movement becomes restricted and torque and drag mitigation strategies are essential. The diagram illustrates how frictional forces act on the string during axial movement. When picking up, friction adds to the apparent hook load, whereas during slack off, friction reduces the measured hook load. Both are direct outcomes of the normal force and the coefficient of friction. This behavior is symmetrical. Friction always opposes motion, whether upward or downward. From an operational perspective, recognizing these trends allows us to differentiate between expected drag and abnormal increases in hook load, which might indicate tight spots, cuttings accumulation, or other downhole restrictions. The diagram illustrates how frictional forces act during axial pipe movement. On the right, pickup is represented by an increase in hook load as friction adds to the string's apparent weight. On the left, during slack off, friction reduces the measured hook load. This graphical representation highlights the dual effect of drag, additive when lifting, subtractive when lowering. Operationally, the takeaway is that friction always resists pipe movement, and its magnitude depends on borehole inclination, surface roughness, and mud lubricity. Even in straight holes, these effects cannot be ignored. The example refers to running a wireline logging tool. How do we calculate the maximum inclination angle at which pipe can still slide into the wellbore under its own weight without mechanical assistance? We start with the given friction factor, mu equals 0.4. We calculate the angle of friction as phi equals arctan of 0.4 equals 21.8 degrees. This represents the angular threshold at which the frictional resistance balances the tangential gravitational component. Next, we calculate the critical inclination angle, 90 degrees minus phi equals 68.2 degrees. This value is fundamental in well planning because it defines the maximum inclination at which a logging tool or tubular can descend under gravity alone. In practice, this means that in wells exceeding 68 degrees of inclination, additional mechanical or hydraulic assistance is required to convey pipe or tools. Methods include using pipe-conveyed coiled tubing, running sinker bars, or selecting lubricating mud systems to reduce the effective friction factor. This slide explains how the friction factor, or FF, is used in torque and drag modelling. It's important to stress that friction factor is not the true coefficient of sliding friction. Instead, it acts as a correlation parameter that lumps together multiple sources of resistance along the drill string. In the field, friction factor accounts for not only contact friction but also other contributing effects such as borehole roughness, micro doglegs, cuttings beds, and even fluid dynamics. This makes friction factor a practical value, calibrated from observed hook loads and torques, rather than a purely theoretical coefficient. Several factors influence friction factor. First, the formation type and grain size determine the natural roughness of the wellbore wall. Second, the type of drilling fluid plays a critical role. Oil-based muds typically reduce friction factor significantly compared to water-based muds due to superior lubricity. Third, borehole tortuosity and support roughness can increase resistance even in relatively smooth wells. Finally, the general borehole condition, including cuttings loading or filter cake, may elevate drag levels. By understanding these influences, drilling engineers can assign realistic friction factor values to torque and drag models. This enables more accurate predictions of pickup weights, slack-off loads, and surface torque, ensuring the drill string design remains within safe operating limits. We compare the friction factors measured during sliding and those measured while rotating. Understanding this difference is important because the mechanical behavior of the drill string changes depending on whether it is in rotation or purely sliding axially. When the drill string is sliding without rotation, the measured sliding friction factor typically ranges between 0.1 and 0.3. This represents the resistance from axial drag due to side forces between the drill string and the borehole wall. During sliding operations, friction opposes pipe advancement and directly influences slack-off and pickup weights. When rotation is applied, the contact points between the drill string and the borehole wall are continually changing. This rolling action reduces static sticking tendencies and spreads the frictional load along the string. As a result, the apparent drilling friction factor typically falls within 0.1 to 0.3, while the back reaming friction factor, measured from hook load changes during upward movement with rotation, can be as low as 0 to 0.05. Rotation therefore serves as a natural friction reduction mechanism. This explains why in practice rotary drilling can advance through high-angle intervals where sliding alone would not be effective. Engineers use these differences to assign appropriate friction factors when modelling torque and drag scenarios. What is being shown here is that friction factors are not universal constants, but depend heavily on the material interfaces and the fluid environment present in the wellbore. The drill string interacts with either formation, rock, or casing, and the resistance generated at these surfaces is moderated by the drilling fluid in place. Pipe-to-formation contact generally generates higher friction factors than pipe-to-casing contact because formation walls are rougher, more irregular, and less uniform. In contrast, casing provides a smoother and more consistent surface, reducing drag. However, if the casing interior becomes roughened by scale, debris, or irregularities in the cement sheath, friction can increase. The role of drilling fluid is equally essential. Water-based muds provide a baseline level of lubricity, but oil-based muds can reduce friction factors by as much as 40%. This reduction arises from the oil film that separates contact surfaces, minimizing metal-to-rock or metal-to-casing resistance. The choice of mud system, therefore, has a direct effect on torque and drag behavior. In practical modelling, engineers must assign friction factors that are consistent with both the contact material and the mud system. Failing to account for these dependencies could underestimate loads, leading to string design issues or unexpected operational difficulties during tripping or extended reach drilling. Now let's take this knowledge and move on to key definitions and how to monitor. Now let's examine the operational definitions for monitoring torque and drag in the field. The first is pickup weight, which is the hook load measured when lifting the string off bottom. It consists of the free rotating weight of the string plus the frictional drag along the borehole. The opposite condition is slack off weight, measured when the string is lowered. In this case, friction subtracts from the string's free rotating weight, making the hook load appear lower. The difference between pickup and slack-off values is a direct measure of drag in the system. Overpull is another critical concept. It refers to the additional hook load observed above the expected pickup weight, indicating resistance beyond normal drag. This is a warning sign of possible hole problems such as cuttings beds, key seats, or differential sticking. Finally, we define the margin of overpull, MOP. This is the design safety margin built into the drill string to allow sufficient tensile capacity for freeing operations, especially when jars are activated. The MOP ensures that additional force can be safely applied without approaching the yield strength of the pipe. A proper understanding of these terms allows drillers to interpret hook load data as an early diagnostic tool. The picture on the left shows the side forces that are applied to the string along a given well path. In the build sections, the side forces push the string to the high side of the hull. In the drop sections, the side forces are to the low side of the hull. Next, if we plot hook load versus depth, we can show the pickup, slack off, and free rotating weights. The pickup line lies in green above the free weight line due to drag, while the slack off line in blue lies below. The gap between them illustrates the magnitude of the drag. Overpull is indicated as an upward shift beyond normal pickup. The definition of torque is the rotational force applied to the drill string at surface to turn the bit. In practice, not all of this energy reaches the bit because some of it is consumed in overcoming friction along the string. Every contact point between the pipe and the borehole wall contributes to torque losses. These losses increase with well inclination, borehole curvature, and formation roughness. In vertical wells with minimal contact, torque transfer is efficient, but in extended reach or high angle wells, significant torque is dissipated before it reaches the bit. From an operational standpoint, monitoring torque trends is vital. A gradual increase in torque with depth is expected as the string lengthens. However, sudden spikes often indicate the accumulation of cuttings, tight hole conditions, or differential sticking. Similarly, torque fluctuations while drilling may suggest poor hole cleaning or reactive shales. Engineers use torque models calibrated with friction factors to predict expected torque at the surface. By comparing measured and modelled values, we can identify abnormal conditions. This predictive approach enables operators to make timely adjustments to mud properties, drilling practices, or string design, thereby avoiding costly downtime. Examining the string on the left, we can observe that torque losses are applied in the opposite direction to rotation throughout the entire string. The torque loss is the sum of the friction factor multiplied by the side forces and the hole size. When we are off bottom rotating, the excess torque is the measured torque at the surface minus the calculated free rotating torque. When on bottom, the calculated free rotating torque is combined with the reactive torque from the bit. The driller should take regular measurements prior to making a connection to note the pickup, slack off, and off bottom rotating torque. This enables the trends to be plotted compared to what is expected. The measurements can be plotted on what is called a broomstick plot, which is a modelled pickup slack-off charts, where the actual measurements give early warning if the trend changes compared to the plan. It is common to run downhole torque and weight measurements. These measurements are calibrated during the same time as the pickup, slack-off, and off-bottom rotating measurements are taken. Engineers use torque models calibrated with friction factors to predict expected torque at the surface. By comparing measured and modeled values, we can identify abnormal conditions. This predictive approach enables operators to make timely adjustments to mud properties, drilling practices, or string design, thereby avoiding costly downtime and ensuring optimal performance. Looking at the string on the left, we can see that torque losses apply in the opposite direction to rotation across the entire string. The torque loss is the sum of the friction factor times by the side forces times by the hole size. When we are off bottom, rotating, the excess torque is the measured torque at surface minus the calculated free rotating torque. When on bottom, the calculated free rotating torque is combined with the reactive torque from the bit. The driller should take regular measurement prior to making a connection to note down the pickup, slack off and off bottom rotating torque. This enables the trends to be plotted compared to what is expected. The measurements can be plotted on what is called a broomstick plot, which is a modelled pickup slack off charts, where the actual measurements give early warning if the trend changes compared to the plan. It is common to run a downhole torque and weight sensor, which sends the measurements in real time to surface. Let's review the sub-module objectives. First, we discuss the applications of torque and drag modelling, showing how these calculations help predict loads and torques in deviated wells and extended reach drilling. By simulating hook load and torque responses, engineers can design drill strings with confidence that operational limits will not be exceeded. Next, we defined side forces and demonstrated how they create normal forces between the drill string and borehole wall, directly generating drag. From this, we introduced the friction factor, a practical correlation that accounts for formation type, mud lubricity, borehole tortuosity, and surface conditions. We also reviewed the causes of torque and drag, ranging from basic frictional resistance to poor hole cleaning, cuttings beds, and differential sticking. Recognizing these mechanisms allows proactive management before problems escalate. We then explained torque and drag monitoring and management, focusing on how pickup and slack-off weights, overpull, and surface torque trends act as diagnostic tools. Finally, we touched on the broomstick plot, a method of graphically comparing measured versus modelled loads to identify abnormal behaviour. We will go into this in more detail later. This concludes submodule 2 of 3. Please proceed to the quiz. Thank you.